Right, so on to today's session then, where we'll be exploring the process of developing a machine learning application from design to execution for official statistics. We're delighted to welcome Daniel Hopp, Associate Statistician with the UN Conference on Trade and Development. As a case study, Daniel will be drawing on some of the innovative work he's been doing on economic nowcasting for global trade data using LSTM neural networks. At UNCTAD, Daniel's been using his experience in data ecosystems, machine learning and programming to help drive innovation in trade statistics, economic forecasting and official statistics. Before joining UNCTAD, Daniel worked in data science and analytics roles in the private sector in tech startups and private equity. So we're really thrilled to have Daniel today. He's got a great presentation lined up, lots of experience and insight to share with us. So yeah, we're really looking forward to your presentation, Daniel. So welcome and over to you.
Thanks so much, Alison, for the introduction, and big thanks to you and the whole team and In-kyung for making this session possible. So I'm going to go ahead and start sharing my screen now for the presentation. So let me know if there's any problems with seeing it. So good so far?
Yes, that's fine. We can see it.
Terrific. So thanks everybody for tuning in. So I'm going to be talking in this session about the design execution of an ML project that we did here at UNCTAD. The format is going to be basically talking about the general outline and how a project like this is executed, while at the same time kind of side by side seeing how those general principles were applied to this specific case study of generating UNCTAD's nowcasts. So I understand that the kind of makeup of this group is very diverse. So there's a lot of people very experienced in machine learning and data science, some people who maybe have not as much experience. So hopefully the contents of the presentation will have something for everybody at every level. So something new, maybe you hadn't thought of before if you've done these projects a million times before. And if you have never even interacted with machine learning in general, hopefully still it will give you some good idea of what actually goes into executing a project like this. So and again, as Alison mentioned, I'm happy to take questions in the course of the presentation as well as at the end. So if you have a specific question about the particular slide I'm on, at the end of each slide, before I move on to the next slide, I'll pause for a moment and ask In-kyung if there were any questions on that. So what we're going to talk about is basically how this whole process was designed and carried out for the execution of the nowcasting application for UNCTAD. So both talking in the general terms of what are the principles that went into the decision making, and then how those principles were applied for this concrete case. So hopefully you see via that kind of two-path structure how these ideas are put into practice. So the sections we're going to go through is the initial problem assessment, assessing whether or not even machine learning is suitable for the application that you're thinking of. Then going through the data gathering process, which is obviously a very important step of any machine learning project, the data gathering and data cleaning and transformation process. Then talking a bit about model research. So really deciding what models and what algorithms and what methodologies you're going to use for your application. Then moving on to, once you've decided on the type of methodology you're going to use, how do you go about implementing that? Then talking about hyperparameter tuning and basically the assessment of performance of different models, which is an important step of most machine learning approaches. And it's something that's maybe not as relevant if you're used to doing more OLS, things like that, which don't have hyperparameters. So hopefully you'll get some information on how exactly to go about dealing with models that have hyperparameters. Then finally going through the analysis of the model's results and how you present those and kind of the final output of this exercise. Then finally, two things that may or may not be relevant for your application, which is the development of your methodology into a library and the development of your results into a kind of a living or website or something more interactive, not just a static report that you do one time. And then finally, takeaways and conclusion from that whole process. So without further ado, let's get into it. So of course, the first thing that you're going to do when you start, oh, and one more thing I wanted to mention, this is going to be a non-technical presentation. So it's really not about any specific methodology, any specific algorithms, or any even specific programming language. It's really more general about the principles as you, in general terms. So what I talk about here is going to be applicable really to almost any modeling approach that you take, as well as to any programming language that you may choose to do your application in. So whether you do it in Python or MATLAB, whatever is your preferred way of working and programming language, these are going to be applicable to that workflow. So starting with the initial problem assessment and basically figuring out whether or not machine learning is even applicable in your case. So that starts with asking the question of what it is you're trying to do. Is this a forecasting problem, classification problem, regression? Do you have time series involved? Is it panel data? So just getting an understanding of your of what you're trying to accomplish here. The next step of that, of course, is figuring out your target variables and explanatory variables. So what is it that I'm trying to model or predict? That's your target variable. And of course, just as important is what am I going to use to try to answer that question or forecast or predict that target variable? And is this type of data suitable for machine learning? Are classical methods more suited to the case, etc.? So once you've kind of gathered all that information and have a solid understanding of what it is you're trying to accomplish, the type of problem it is, and what your inputs and outputs are going to be, then you can start to lay out a project plan, which I recommend doing from the beginning. So having a good understanding from the very beginning of your project, what the scope is, what your final goals are. Is this going to be a one-time research paper? Is this going to be something that you will build out into a recurring, let's say, weekly updated model that the public can interact with? Do you have a good idea that this will work out in some way, or is it just a really exploratory project? Is it going to be for internal or external use? So these are all the things to have in mind from the beginning, because that will really help later on in following the correct steps and making sure that you're not caught out later on in the project and have to go back and rewrite things substantially because you didn't anticipate that you would have to go back and change things or add things, maybe even a year down the line. So I recommend having that all laid out from the very beginning. And another thing that I want to kind of recommend is the use of version control at GitHub. I understand probably from the makeup of this audience, many of you are already doing this, but of course, oftentimes in the official statistics, GitHub and version control is not as emphasized. So I just want to kind of promote the use of that. So if you're not familiar with what it is, basically it's having a history of all the changes you've made to your code over time. Obviously, it's very rare that in the course of developing your project, you have a very direct path from start to end. There's going to be a lot of twists and turns and trying different things, dead ends, etc. That's very common in machine learning projects. So if you have something like GitHub where you can create branches, where you're trying out a different model and it doesn't work out, you haven't sort of messed up your original model. I think I personally experienced it many times before I started using GitHub, and I'm sure many of you have as well, that you have a working model, you have something that's good, you want to try something new or additional to it, and then it doesn't work out, but you've kind of gotten away from your original working model, and it's then becomes a whole new project just to get back to that working state. And that's what GitHub and version control is perfect for. You basically don't have to worry about that anymore, and any mistakes or rolling backs that you want to do just become very easy. So I would really recommend that if you have any interest in starting to do more machine learning in your work. So what this meant for the nowcasting of global trade problem was, of course, first assessing what it is we were trying to accomplish with the project. So the goal was to nowcast global trade. This was a regression problem, so forecasting the growth rates of global trade. It's using economic data, almost, well, so time series, everything is a time series. And the idea behind nowcasting is to get a advanced read on a metric before the actual figure is made public. So while the aggregation and the correlation is happening, you can already have an idea of the target variable well before, based on other data that are published more quickly. So this is a kind of a special case. Nowcasting in general, there are some special data characteristics. So what we had to look into is, what are the standard methods of performing this type of thing? And in your problem, that would mean looking into, do people use decision trees for this type of problem? Do they use neural nets? Is OLS going to be sufficient for your case? So this is that step of figuring out whether or not even ML is the proper way to go about addressing your problem. And then in the course of creating this kind of workflow for the nowcasting application, we had in our mind from the very beginning that not only are these models going to be, initially trained and having the outputs, but they're going to be updated and evaluated on an ongoing basis. So the data needed to be updated on an ongoing basis. The predictions needed to be generated on an ongoing basis. The final results, so the final plots, etc., all had to be published on an ongoing basis. So from the very beginning, I could take that kind of requirement and keep it in mind, so that everything I did had that goal in mind, and everything I did could be easily extended, built upon, updated, etc. So any questions there, Ying-Kyung, before I move on to the next slide?
So there's no question so far.
Perfect. So hopefully that gives you a little bit of information if you haven't dealt with machine learning projects before, just even at the very beginning, what to do and how to set up and kind of get to terms with the problem that you're dealing with. So the next question you might ask yourself once you've decided that, or once you've figured out what your target variables, et cetera, are, is whether or not you even want to use machine learning for this problem. So machine learning is a pretty broad term. Depending on who you ask, you're going to get different answers every time. Even something like OLS can be considered machine learning. It just depends on your definition. But in more, when we talk about it, probably in the context of this working group and in the media, et cetera, machine learning generally involves much larger data sets, either in number of features or the number of observations, than you probably usually see in official statistic work. So less surveys and more, big data, that kind of thing. And then often it's dealing with independent observations. So things like photos, search results, these kind of industry applications. And then also the important thing to think about is that often in machine learning, the focus is more on inference and, say, predictions over causality and, precise coefficients. Especially, in my time working in the private sector, the metric for success is always about inference and predicted performance, and there's very little emphasis placed on causality and why the model says what it does. It's really about taking those predictions and using them. So looking at that nowcasting application and how machine learning could be applicable in that case, of course, we first started by looking at the existing literature on nowcasting and the methodologies that are used there. So this is a place where kind of that line between machine learning and traditional statistics is very fuzzy, because there exists a lot of commonly used methodologies for nowcasting. One very common one is the dynamic factor model. And dynamic factor models are as much machine learning as any other, neural network or or decision tree, boosted trees, etc. In my opinion, it's more about kind of the space that they're used in. It's more used in academia and in the international community, etc., rather than in private enterprise. So it's not often going to be labeled machine learning, but the principles are really the same. So having identified that approach, that we wanted to use this traditional approach, at least to start with, I also decided to try out the use of neural networks for this application. So that was something that was mostly born out of curiosity, and yeah, to see whether or not the neural networks could be applicable in this application. Basically, everything I say in the rest of the presentation could be applied to a project where just the dynamic factor model was used. The same processes are going to be used, etc. But this application has the additional kind of aspect of simultaneously trying out this more novel approach in the neural networks and that element of comparing the performance of that methodology to the more well-established dynamic factor model. So that's how kind of the approach in terms of the modeling was landed on. Are there any questions, In-kyung, before I move on to the next slide?
No, there's no question so far.
Great. Hopefully that means everyone is understanding everything very well. So once you've decided on what it is you're trying to estimate and how you're going to go about doing that, the next step, of course, is actually getting that concrete data, actually getting the information that's going to be fed into your models. So, of course, you're going to make sure that you have a way to get your target variable, the history of your target variable, and then as well, looking into variables that are potentially related to that and could have some kind of relationship or predictive power on your target variable. And in this stage, I would recommend really kind of the more the better. You can't go wrong with too much data, and it will give you kind of a bigger sandbox to play in later on when you're tweaking your model and looking into creating the best performing model. So more is always better. That's kind of always the mantra of machine learning, because you can always cut away later on. But if you have a poorly performing model, to add in new variables later on is going to be more work. And then another thing to think about at this stage already of the data gathering is whether or not you will be repeating this activity in the future. So is this really a one-shot thing where you're just exploring the feasibility of an approach, or will this later on be built into a recurring project where you update the model on an ongoing basis? Will you want to revisit the model later on to retrain it and potentially retweak it and re-optimize it? Or is this just something you're going to do once and kind of never look at again? I would say, in my experience, that you should usually err towards the latter. I think it's very common that you start out exploring something and thinking that you're only going to do it this one time. So I'll kind of do it the quick and dirty way. I'll just download my files manually for this one time. But often what I have found happens is that later on, you want to expand on that, even if you hadn't initially anticipated that. So I think it's good practice to kind of keep that in mind from the very beginning and do your data collection process in a sustainable way, in an updatable way. I'm sure we've all been there where a year later, someone asks you for the updated version of those numbers that you kind of just haphazardly got together from writing your code in as if you were only going to do it once and then kind of struggling to recreate exactly what you did last year. So if you just keep that in mind from the very beginning, it really helps you out later on. And then, of course, the step of cleaning your data and making it in the format that your particular methodology requires to be accepted. So if you're dealing with neural networks, you maybe will have to scale your data. If you're dealing with decision trees, you can probably stick with the original untransformed data. But this is all going to depend on the methodology that you are going to use. Making sure that all your data have the same frequency or units, just all these type of things. That's called data wrangling, and it's a commonly held or commonly repeated adage in machine learning that 80% of your time is actually spent on gathering your data and transforming it, wrangling it, getting it the way you need it to be, and really only 20% of the time is spent on what we traditionally think of in data science and machine learning, which is, tweaking your models and getting your outputs, interpreting your results. But really, this step of gathering your data is a kind of an underrated one, and it really takes a lot of time. So for the nowcasting application, what that meant was, of course, first starting with researching variables which were related to global trade. And then at the same time, keeping in mind that we wanted to update this on an ongoing basis. So making sure that the sources that we used would be consistent, would continue publishing into the future, that the way we got the information was, again, kind of consistent and easily reproducible and easily automatable into the future. So that means, not downloading tables from databases, but rather using the API, making the manual process of updating your data or adding a new data set as automatic as possible for future use. So if you want to update your model, that it can be done automatically or very quickly, as opposed to having to run through your 45 variables, getting the latest CSV, renaming it the proper way that you had it named, et cetera, et cetera. So it's really important to keep that in mind from this early stage and really using APIs as much as possible from the beginning. Any questions there on the data gathering process, In-kyung, before we move on?
Yeah, there's no question on the chat yet, but I have one question. And
Sure.
I think what you mentioned about 80% of time being spent on the data gathering and cleaning can be very relatable to many people working on the machine learning and data science. And I wonder how your experience went in terms of this process. Did you also work with the what would you call a business owner or domain subject matter expert to gather what kind of data or feature would be interesting for your problem and so on? And how was the process of gathering the data? Was it easy to gather within the organization, or you have to go through, I don't know, some kind of authorization or something like that yourself?
Right. So that process of identifying potential input variables to the model was actually started by my predecessor, Fernando Cantu, who I'll mention a bit later in another section of the report. So he had started basically that process of identifying those variables and the data sources, et cetera. And the data sources, most of them that we ended up using are from standard sources like OECD is a big one. They have a lot of great information on economic data. Things like the World Bank was another big one. And so those luckily have public APIs, so we were able to get that data very easily without any authentication or having to deal with any business owners. We examined a lot of other potential data sources with private companies, with pay databases, et cetera. So we did a lot of testing on that. And there are a couple sources which did end up making it into the final models, which are a bit more, let's say, non-standard, in the sense that they didn't come from the OECD or the World Bank with their nice APIs, but rather from, let's say, the Hong Kong ports website. So these ones had to be kind of more specifically considered. So it was a long process. As I said, probably in this case a bit less than 80% because there was a lot of novel modeling going on at the same time, but it was a substantial chunk of the work was to just get all these variables, get them in the proper format, make sure that they could be got on an ongoing basis and not just finding one random PDF somewhere and typing in the information. It had to be really sustainable. So some sources that we found that ended up look like they could be useful, we decided to drop just because of the unreliability of getting the information into the future. We couldn't guarantee that we would be able to use that information on an ongoing basis, so we didn't want to create models that had dependencies on these kind of shakier data sources. So that's how that process came together. Of course, I'm glancing over a large portion of it, but hopefully that answers your question to some degree. Great. So
one more question.
Yeah, please.
Yes, like how like you narrowed down the like variables which might be impacting the target variable.
Mm-hmm.
Like there could be like 100 of data points, so you must have somehow narrowed it down. Okay, these
Yes.
10 points will be impacting the target variable. So how was it done, this part?
Yes, exactly right. So that's actually, I believe, even not quite the next slide, but in 2 slides, I'll be going over exactly that. So as I mentioned earlier, the idea was to get as big of a data set as possible, with the idea that we would cut down on that later on. So at this stage, the data gathering stage, we really were kind of grabbing everything that we thought could be remotely related to the target variable. And then in 2 slides, I'll talk about how then we took that big almost 200 plus potential explanatory variables and how we winnow that down to the ones that we actually ended up using in the end. So hold on for 2 slides and I'll get to exactly that.
Okay, got it.
Yeah, so once you have your data, of course, the next step is going to be, all right, I want to use this data to train my model, generate my predictions, create my inference, etc. So hopefully you've thought about this a bit from the earlier on in the process, but you think about suitable models for your problem type, this a regression problem or a classification problem. Then once you've found the methodologies that you're interested in trying out, and again, this could be multiple. It doesn't, for in this case, at the nowcasting case, we did use multiple methodologies to kind of compare to each other. But it could be that you just have one that you've decided that whatever OLS is the best approach and you're only going to do that. I would recommend trying multiple methodologies in a machine learning context because different applications can be suitable for different types of models. And if you create your process in a way that it's easy to try out different types of methodologies and compare them to each other, it's always better to have that kind of validation aspect in your process. So once you've decided on the methodology or methodologies that you've decided you're going to use, you then have to think about how are you going to actually generate your predictions? How are you actually going to train these models? Is there an easy to use existing implementation in your programming language of choice? Or will you have to code this up yourself from scratch? So this could be either because your methodology is novel in the sense that nobody has ever coded up this exact type of model before, or it could be novel in the sense that nobody has coded it up in your language. So if you're a Python user and there's a great library in MATLAB, but you're going to be using Python in your workflow because that's how your data is gathered, that's how you're going to generate your charts, etc., and you want everything to be in Python, you might have to recreate that library in your model of choice. So that's another thing to keep in mind and be aware of at this stage already. And then, as I said, it's good to be able to try different types of models and compare their results. That might be not feasible if you're already going to have to do a lot of work for just your first methodology of choice, if there's not a good existing library. And specifically in Python, the sklearn library is very good for all this type of stuff, pretty much anything machine learning, but it has many, almost all of the most popular machine learning algorithms are there with a common syntax. So it's very easy to try different approaches. So if you find yourself, if you're a Python user and you find yourself where you can use sklearn, you could potentially try very many different types of methodologies with minimal actual change to your code structure. But that's, again, going to depend on your language of choice and your problem. So what this step meant for the nowcasting application was identifying whether or not there existed a dynamic factor model implementation in the programming languages that we were using for this project. So that was R. So the whole data gathering process, etc., was all done in R. So everything was going to be in R. So we did some research together with Fernando, who, again, I'll talk about it a bit later in 2 slides, I think, identified the specific type of dynamic factor model we wanted to use, which was made thankfully public by the New York Fed when they published their own paper on nowcasting. So we could actually go through, find their MATLAB code, and we basically had to transcribe it over into R. So this was a big process, and I'll mention it a bit later when I talk about kind of creating libraries from your code and making it publicly available. But this was a big step to transcribe that dynamic factor model code from MATLAB into R. And then for the second methodology, the neural networks one, that basically had to be coded up entirely from scratch. So the project began with me just kind of researching neural networks with time series. So which type of neural network was most relevant or best at working with time series. Stumbled on or found the long short-term memory network architecture, which is the probably the best neural network architecture for dealing with time series. However, that architecture is mostly used for things like natural language processing, speech recognition. So basically a completely different domain from the economic nowcasting that we were doing here at UNCTAD. So that meant that there were general libraries of how to code up a long short-term memory network, specifically in PyTorch, which is a deep learning framework, together with TensorFlow. Those are the two kind of the biggest ones. But there was it was very general, and so very difficult to actually get to work with the economic data for our specific needs. So this was a lot of work to actually code up this generic PyTorch LSTM implementation into something that worked well for economic time series. So that had to be created from scratch as well. Yeah. So what I'll mention here is that this stage is where I already had in my mind that I wanted to make these implementations publicly available. And the motivation is, from the beginning, was that even for myself as a statistician and as a user of the methodologies, it's very likely that I'm going to want to use these methodologies again in the future. So I had to resist the urge to just code up something very specific to this particular use case, which, for example, the MATLAB code from the Fed was very specific to their even environment. So specific to the type of data they were working with, their columns, even in some cases, etc. So from the beginning, I had this in my mind that I want to make this as general as possible, so that even if for other people it's not particularly useful, I know that as a statistician at UNCTAD working in nowcasting, that probably I'm going to want to apply these methodologies to different problems in the future. So from the very beginning, I developed them as separate local libraries from the rest of the code about getting the data, analyzing the results, etc. I made them modular from the very beginning as local libraries. And then I'll talk a bit later on how that made it easier for me at the end to repackage them and make them into publicly available libraries. So are there any questions on the implementation of the models that you're going to be using before I move on?
So actually there's one question, but I think it is about the previous slide about data gathering process. Mm-hmm. So the question is, are we talking now only for the data for training purposes?
So no, not necessarily. So of course you need, it's basically the same, you're going to need the same data for both training, testing, and then your future inference on unseen, future observations. Every machine learning algorithm is going to require the same inputs later on to test on novel data. So you're going to need to be getting this information in a sustainable way, because you'll need it later on for inference on unseen observations. So it's really the same exact process for your training and your test data. The only difference is that at the model selection phase, which I'll talk about in 2 slides, you're going to be cutting up this data that you've gathered and making some of it into your training set and some of it into your testing set. And that is kind of a heuristic step, not arbitrary, but there's some percentage that you're going to want to use for training and for testing, which I'll talk about. But the data gathering process is a universal one, and it's the same exact steps for both training and for testing and for future inference on completely unseen data that maybe hasn't even been produced yet at the time of your training of the model. So that brings us to model design and selection. So once you have the way that you're going to train and predict from your model, so the actual implementation in R or in Stata, whatever your programming language of choice is, you then have to actually start training models, generating predictions, and training hyperparameters, so picking hyperparameters rather. So if you have a lot of different both potential explanatory variables and a lot of different potential hyperparameters, you need some way to compare different models' performance to each other. So in a machine learning project, you're probably going to be running hundreds, if not thousands, of different models with different input variables, with different hyperparameters, with different even methodologies. So you might be comparing, well, in this case, comparing the dynamic factor model to the neural network. So you're going to have lots and lots of models, and you need a way to basically quantify and compare these models together. So you have to define your performance criteria and make sure that you create a sustainable process for fitting and assessing many different runs from many different models and saving that output somewhere so that you can go back and analyze it later on. So concretely, what that meant for the nowcasting application was the fact that we started out with, as I said, this large pool of potential explanatory variables, over 200. Of course, the best model probably isn't going to be the one where you just throw every single variable into the model. Most, you're going to have problems of overfitting. Some models may not even be able to handle that many input variables, depending on the methodology you're using. So you're going to have to do some sort of model selection on the potential variables that are going to be going into your model. For the LSTM, this is a methodology that has hyperparameters, which means that kind of different macro parameters on how the network is structured, how many hidden layers you have, how many batches per training epoch, et cetera, et cetera. These are just things that make the model behave in a different way. And so you can't just train the default model and assume that that's the performance of this methodology, because it can vary widely based on the hyperparameters you use. If you've ever used a decision tree, they have tons of hyperparameters, which can really change the quality of your model. So for the LSTM, bearing in mind those hyperparameters, we use something called grid search, which is where you have a list of all of your potential hyperparameters, and then a list of all the potential values for each of those hyperparameters. And then what you want to do is run the model for all of the different permutations of those hyperparameters and save the performance of them, so that later on you can pick the best performing model and the best hyperparameters for your use case. And for that process to happen, you have to make sure you're saving the performance and the hyperparameters of each of these models to a CSV or some way of saving it, so that you can look at the performance later on and make your decisions, tweak your models, really assess your models and the hyperparameters. So a little bit of logic on the approach that we took for the nowcasting one. We used a lot of random sampling. So the idea is that out of the 200 odd potential explanatory variables, there's obviously way too many permutations to test all of them, to find the absolute best combination of variables for this problem. That would take way too much computing power and time. So the idea from taking random samples of explanatory variables was to not find the absolute best model, but to find a better performing model on the distribution. So if the universe of all the potential combinations of explanatory variables is this red distribution, the idea was to take a lot of samples. So in this case, it was over 500 random samples of subgroups of explanatory variables. And then you'll generate some sample distribution, which is obviously not the real distribution, but it's some representative sample of that real distribution. And then by picking the best performing from that sample, you have an idea that, okay, maybe I haven't picked the absolute best model, this one way over here to the left, but I've picked, relative to all my potential combinations, a very good performing model. And that's the logic behind that random sampling of all these potential explanatory variables. This is just one approach to that question. There's a lot of different ways to go at it. A lot of methodologies even have this idea in mind. So something like a random forest has a parameter for taking random sampling, subsample of your explanatory variables for each of its different trees. So there's a lot of different approaches for it. This is just one, and this is just the one that I employed for this particular case. If anybody knows any better approaches to it, please speak up either now or at the discussion in the end. But this is at least a way to have a relatively solid idea that you have a well-performing model out of the whole world of potential models. This is super useful in machine learning because a lot of times in more classical statistical problems, if you read a lot of papers on more classic statistics, the explanatory variables are often given as a static given. So you have these 10 explanatory variables, and that's all we'll say about what's going into the model. We pick them by hand. That's what they are. So just accept that. And so the idea of taking many more in the random samples is that by taking those specific 10 input variables that you picked out heuristically, you could have some sample of the world of potential models over here in the middle because you forgot about this whole relevant category of explanatory variables. So by taking as many as possible and doing a lot of sampling, you can at least hope to move a little bit more to the left of that performance. And what I will mention, what I wanted to say about Fernando's work is that he's working on a paper dealing with kind of exactly this topic. So a more quantitative and deterministic way of selecting the variables that go into your model. He's still working on it right now. It should be finished sometime either late 2020 or sorry, 2021 or early 2022. So keep an eye on his work. I think it's an under talked about topic in official statistics, so I'm looking forward to seeing what he finds. I don't know the specifics of the methodology, but hopefully we'll be able to look at that soon. So hopefully that answered the question from earlier to some degree. Did any other questions come up or any further explanation on this?
Yeah, there's one question about the grid search. So the question is this the simplified grid search useful only for LSTM, or is it there for other scikit models?
Yeah, so it's actually relevant for almost every machine learning algorithm that takes hyperparameters. It's a universal concept, and if you look in sklearn, they even have pipelines. They have implementations of grid search that are generalizable, where you've given a dictionary of your potential inputs, or sorry, potential hyperparameters and the potential values for them, and then it's like a one line of code to run the model, try it with all the hyperparameters, and spit out the outputs. So it's a very well-established concept. If you even just Google grid search, you'll find a lot of great information on explaining it in more detail and better than I can here. So it's not specific to LSTM. It's a universal machine learning topic, basically.
Yeah, and there's another question about I think variable selection. So the question is, does regularization not fit this framework?
It should. So that goes on earlier to the data transformation step, and it depends on your methodology and whether or not regularization helps for that type of algorithm. So that's going to be on a case-by-case basis, and it still should be relevant for that case. Sorry. So the next thing I wanted to show you guys was just a very concrete example of what I mean by having all these different model runs and storing the results. So what I have here is a screenshot of one of my results CSV files and how I'm storing that information. Of course, there's different ways to do it. This is by no means the best way, but it's just the way that I've been doing it, and I have found it to be adequate for the task. So basically, what it's doing is saving all of the relevant information for each of my model runs. So information like the type of methodology I used, which target variable was used, the explanatory variables that went into the model, and then most importantly, or also importantly, the hyperparameters that particular model did. So with the information from here to the left, that means that I can recreate any of these models later on. And then the second aspect of it, so that's the first one, making sure you have all the information you need to recreate any of your models. The second aspect is then capturing the performance of each of those models. So again, you will have defined your performance criteria earlier on. So it could be mean absolute error, it could be root mean square error. It's a different metric if you are doing classification. So you'll know what you need to use as a performance metric based on your application. But in this case, for this regression problem, I was saving both mean absolute error and root mean square error on both the train and the test set. So in case you're not familiar with most people here probably are, but if you're not, the concept of train and test sets is the idea that you may train a model that does fantastically on the data that it was trained for. However, when you give it new information, so let's say you trained a model from 2000 to 2010, and when you look back at its performance, when you give it that information, it's getting everything almost perfectly right. But then when you give it information from 2010 to 2015, it's terrible. It's completely overfit to your training data, so the data that went into estimating that model, and it does not generalize well at all. So that's kind of the whole logic behind having a test set. So that's keeping a certain subsample of your data out of the training phase so that it's information that the model has never seen before. And then you can have a much better idea of the generalizability of your model to new data into the future. Because at the end of the day, that's the goal of most machine learning applications, is being able to use the model for more information in the future. So for each of these model runs, I was saving the mean absolute error and the root mean square error on both the train and the test set. And what that meant is that later on, I could go back and analyze these figures and figure out which model was doing the best. So generalizing and giving me the highest quality predictions. Any questions on this, storage of the results of the model runs, or how that's generated, or why it's important before I move on, Inkyung?
Yeah, there's one question.
Mm-hmm.
Did you not use cross-validation when evaluating the model's performance?
Cross-validation?
Yeah, cross-validation.
I'm not familiar with that term, so yeah, I'm not sure. So what I used was the on the test set, and what was an issue, or sometimes is an issue with time series data, is that the you can't your observations are not independent, so you can't take many. It's called folds, k-fold validation, if you've ever heard that term before. But the idea is you take random subsamples. If you have independent observations like photos or whatever, you take random subsamples, train a model on the training data, do it on the test set, and then you do this 10 times so that you have a better idea. But for time series, it's not relevant. So does that answer the question? I haven't heard that particular term before, but maybe the asker could explain it to me.
Yeah, what you mentioned, the k-fold cross-validation is very similar concept, but I guess your answer is that since it is time series, it was hard to subdivide for other type of data. Okay.
Right. Yeah. For this particular application, it is not as doable because of the time series aspect. But if I had independent samples, for sure, that's a very important step, is cross-validation. And it just gives you a higher confidence in your results you know that it's more more generalizable, because with the time series and having only being able to train on the earlier data and testing on the later data, you could have situations where you just got lucky, the model just got lucky, and it won't generalize into the next year, etc. So it's a bit harder to test that for time series, but for independent data, you should definitely do this on many different random subsamples. So what that would mean for this, so say that these weren't time series, each of these numbers would not be the result of one single model on one single train and test set, but on 10. I think 10 is a very common number. So it would be the average of the performance on 10 random subsamples of test data.
Yeah, and there's another question. Did the use of LSTM deep learning improve a lot the fitting compared to the other linear or classical methods?
Yeah, so I'll talk about that more a bit more in the end, because I have done a whole presentation on that process and the results. The short answer is that it did improve. I don't know if significantly is a subjective term, but it did improve on the performance of the dynamic factor model. But there's a whole paper, research paper that I linked to at the end here about the results from that exercise. But yeah, the short answer is that it was a very successful implementation. But I'm happy to go into more detail on that particular project at the end for when we have the general discussion. But otherwise, I'll move on to the analysis and presentation of results. So at this phase, you're kind of finished your whole modeling. You have your results. You have your best performing model, etc. And you now move into that phase of writing up these results. So this obviously is going to be highly dependent on your use case. And the purpose of the analysis, was this for a research paper that you want to be published in a journal? Was this for a report? Was it for an annual report that's going to have to be rerun next year? Is it a pilot study where that's a one-off and you will take that idea and potentially apply it later on, but not in the near term? Is it for an internal study that's just going to be shared with colleagues? So obviously, you guys all probably know, but so any of these use cases is going to be a different process in how you present the results of your modeling. So what I can recommend internally, so if you're going to be sharing these results with your team or kind of less officially, then Jupyter Notebooks and R Markdown are very good tools that let you present both code together with plots and text analysis all together. So it's a very nice way to present the results of your modeling. And then obviously, if you're going to be doing it externally, then you'll coordinate with your publication team and make it sure it's the format that they need for reports, etc. Just one thing I'll mention is that it's super, and again, people here probably know this, but it's super useful to analyze not only that, or to make the code not only for your modeling and data gathering step, but also for that final kind of last mile where you might be most tempted to just play around and tweak your plot and get those final results you want for your graphs in your paper and your tables, etc. I think it's pretty important that even that step is highly thought out and reproducible, because I know me personally, it's been many times where I take my results, code up a very bespoke output, and then think, great, I'll plop that in the report, good, but then later on, I need to change something, or I need to add another plot, or I need to tweak something, and then I'm struggling with generalizing the model, generalizing the final results, and basically recreating those final outputs for the paper, for the table, etc. So I think the moral is just really to always write good code and always keep in mind that you almost certainly are going to be coming back to this. So don't take any shortcuts. For the nowcasting model, there were basically two different goals or outputs from the exercise. The first was just to pick the best performing model, dynamic factor model, to produce and use for UNCTAD's nowcasts, which are published in a quarterly bulletin. So the idea behind that was just to find the best performing dynamic factor model, which is a well-vetted implementation used for nowcasting, used by a lot of different organizations, etc., and take that best performing model and update it on an ongoing basis to be published as UNCTAD's nowcasts. The second one was to basically write up the results of this comparison between the LSTM and the dynamic factor model. So that, of course, is much more experimental and took the form of a research paper. And it just has a different goal from number one, which was just to pick the best performing model with a vetted methodology to use as UNCTAD's nowcasts. So for the first one, once I had that results CSV I showed you guys earlier, it was a pretty simple process to choose the best performing model on that information, code up the final process from start to end, updating the data to getting the predictions, and automating that to let it go every week so that every quarter when time came to produce the next bulletin, I would have the latest data and the latest predictions for the relevant quarter. For the second one, that involved doing a whole analysis comparing the two methodologies together and then writing up those results into the eventual UNCTAD research paper, which I'll link to at the end of the presentation. So this step, again, is very bespoke. It depends on your application, but that's kind of the last thing to bring it all together. Unless you want to go a step further, which I'll talk about in the next two slides. Any question on this, In-kyung?
Yeah, there's no question on the chat, but I have one question.
Mm-hmm.
So you mentioned about using the nowcasting model for like every quarter or so.
Mm-hmm.
Then how do you retrain your model once it is out? Do you monitor data or model for like any drift, or is there a schedule already planned?
Mm-hmm. So the idea is basically so the model is retrained each quarter for that quarter's. So let's say we're in nowcasting 2021 Q4. The model was just trained on all the data available the latest data available, and then now that's the model being used for 2021 Q4. And then when 2022 Q1 comes around, the model will be retrained again with the latest data available at that time, etc. And then once a year, this is again a bit arbitrary, but it depends on your resources and your use case. But what we decided together with Fernando before he left was that once a year, this modeling exercise would be re-performed. So that means the sampling of random explanatory variables, etc., just to confirm that on the latest information, especially now with COVID, that the model is still performing well, that there isn't now one that performs better in this new, kind of environment we're in. So the idea is that the model is retrained every quarter with the existing, hyperparameters and explanatory variables, and that once a year, a more extensive reassessment of that whole process is undertaken to make sure exactly that there's no drift, that what used to be a good explanatory variable has now become worse. And so the hope is that once a year is often enough that the drift can't get too far in that time period, and that if something does need to be updated on a more substantial level of the model, that will happen in that yearly review process. So if there are no more questions on that aspect, I'll move on to the development of the library, of a library from your work, basically. So the idea, I touched on it a bit earlier, but again, the idea is that if you had to do some novel coding for your methodology, that you should think about making this either a publicly available library, or at the very least a library for internal use at your department or at your organization. So this counts whether or not you have coded up an entirely novel methodology from scratch, or if you just made a new implementation of an existing methodology in your particular programming language. So both of those cases could be useful either to yourself or other people into the future. So it's nice to modularize that and make it accessible outside of the context of this specific project where it was developed for, basically. So that's something that ideally should not happen just at the very end, where you have to go back and pick out exactly what is the core functionality of the methodology. But ideally, you think about that from the very beginning, and you keep that modularized from the very beginning. So you want to make the library or the code for the actual methodology itself as generalizable as possible. So modularize as much as you can, make anything specific that needs to be specific, a parameter for your functions, etc. And that's just going to make it a lot easier for you later on to make it publicly available. So concretely, how that played out for these this nowcasting exercise, it was relevant for both the R implementation of the dynamic factor model as well as the Python LSTM library, and later on the R LSTM library. So having in mind that this was a methodology that I might want to use in the future. So again, it started out in the beginning just for myself. I knew that I might want to use this LSTM methodology if it was promising for different applications in the future. And I didn't want to have this be siloed in this particular project, depending on this particular file structure, this particular data set, etc. So I really wanted to make that as standalone as possible from the beginning. So that meant that as I was coding up this whole project, I kept that functionality separate as a local library, so as a separate import statement, and where that code was as generic as possible in a different file. And that meant, so by doing it like that from the beginning, it meant that at the end, when I had wrapped up the analysis and had the research paper, etc., that to make that publicly available, all I had to do was go through that core functionality, clean up some things, the syntax and etc., add a lot of comments and documentation, and then finally add concrete examples, and then follow the standard procedures for releasing a Python library or an R library. And so since I had been thinking of that from the very beginning, it was very simple to do that and hopefully help other people who are curious to try out the methodology. So I know from personal experience, a lot of times people will talk about their methodology employed in their paper, and I'll read it and say, that looks great. I want to try that out on my application and see if that's the right way to go for me. And then I look into it and I see that there's either no implementation available to me. I would have to code it up from scratch and read their math and make sure I did everything exactly right. Or it's very specific to their project and I'm not going to easily be able to implement it myself. So the goal by making a public library that's generic is that someone could read the research paper on the LSTM, say, wow, that's pretty interesting. I'm interested in trying out an LSTM for my case, which could be unemployment, it could be something completely different from the original case. But because there's that very generic library, they can try it out very painlessly. So that's kind of the idea and the goal. And I think that in general, if people did this more often, it would be a real boon for the community. I think it's starting to become more of a thing to make your code publicly available. But that's just kind of the first step. The second step is both making it publicly available and easily implementable, so easily usable by a new person who has no idea about the specific context from which it came. So does anybody have any questions on that concept or idea or anything about that?
There is one question about the retraining again. Mm-hmm. So the question is, do you keep track of the selected variables between retrainings, assuming that the variables change between the quarters?
So I have all the history of all the models ever run with the training period and test period, etc. The first exercise, so the first reassessment of the model is going to be happening right about now, actually, in October. So I haven't gone through that process yet. But for the retraining, yeah, everything is saved. Of course, I will be comparing what I'm currently using on the new data, and that will go in as another potential option, and it will be compared to the other ones that come out of that analysis. And we'll see whether or not these continue to be the best variables for the job, or if something else comes out of it. But I'm not sure if I answered the question. Hopefully.
Maybe, well, Daniel, maybe it's easier to explain with words rather than
Sure.
typing.
Yeah, sure.
Because I'm also very slow in typing. No, I think this is a question beyond, let's say, the mechanics of this machine learning. More, let's say, as an economist. So if there are variables with different forecasting power, let's say, between quarters, that may actually have an economic interpretation there as well, especially in this, very volatile period that we're all going through. So, I mean, that's a little bit more the background of that question, whether there would be some story in there as well to tell.
Yeah, so the economic kind of story is going to be explored in the October kind of revisit, and then seeing, if one of the variables drops out, kind of potentially thinking about why it dropped out, and if a new one comes in as a more performing, examining why that might be introduced. So I guess kind of like a post-mortem you're almost talking about. So some analysis of if the inputs to the model change and some things have different power now in 2021 as opposed to pre-2020, why that might be from a causation perspective. That would be probably something that will happen internally. I'm not sure if we would publish that as like an analysis of the nowcasting model is changing, and here's potentially why that may be. We're still learning in that regard. I'm not sure what the best way to communicate that if the model does change may be, but it's an interesting point and something that we'll consider when that exercise does happen. So finally, what I'll talk about is the development of a final data product. So what I mean in this regard is going one step beyond a paper or a report where you write up your results and taking the next step to something more kind of living, where whether it be a website or a portal or a monthly email newsletter, just some way that that your model and that your exercise can become something living and something more than just this static report. It could also just be a periodical report. So in this sense, what you would want to think about is if there are potentially additional ways to display results or add value to them. So one common thing that people do is create an interactive website, or at least a static website, but that is updated on an ongoing basis so that people can explore themselves, be able to check out the latest updates of your model without having to wait for some sort of official update, etc. And for accomplishing projects like this, usually you're going to want to start with a prototype, so a proof of concept, let's say. And depending on which kind of ecosystem you're operating in, Shiny Apps is a really great option for R. So you can create free interactive websites based on your models and your code and your data that actually can look pretty slick sometimes. So you might even be able to use a Shiny app for a final kind of production public-facing website. But at the very least, it's good for internal prototyping. And then for Python, Bokeh and Heroku is a good way to host. So to create your application, so to create the interactive data product that you have, however it may be relevant for your project, and then using Heroku to host it. But of course, once you have that prototype and this kind of proof of concept, you can bring it to the next level and work with the developers on your team to develop it into a proper website, official website. And what I'll just say about that process is that it's important that your whole workflow and process is automated and ideally can be run on a server, because you're not going to want to have to deal with updating this thing manually on an ongoing basis. It's going to be a huge pain in the butt. So the best kind of solution is that you're going to have this process that runs remotely on a server, is automatically updating this website, and you can kind of set it and forget it, maybe have some error reporting in case something goes down or some kind of new unexpected value in the model breaks things. But that's something that you can largely set and forget. Because if you start to create these that depend on manual steps, it's going to become unwieldy very quickly, and it's probably going to limit how many different types of data products you can actually get out in the end. So just keep that in mind. So for this nowcasting application, what this meant was taking inspiration from the Fed's presentation of its own nowcast, which I'll show here so you get an idea of what I mean by kind of going above and beyond just a report. And so you can see, give an idea of how you can transmit the findings of your model in a more interactive, living way. So this is the Fed's nowcast, which they update on a weekly basis. You can see how it's a quarterly GDP nowcast. So you can see how the quarter's GDP is being forecast over time. And you can see what data releases are contributing to the changes in the data, or sorry, in the forecast. You can see different quarters. So, okay, how was quarter 2 2020? And so if we go to 2020, you can see some of the craziness that ensued in the second quarter of 2020, where earlier on in the quarter, they were thinking, okay, not too much going on, maybe low growth, 1%, 2%, and then plummeting to 30% declines as the COVID set in. So it's just interesting to be able to interact with the product of the model in a more kind of organic and real tactile way, to read about their methodology, FAQ, etc. So the idea now is to take that idea and create something similar for UNCTAD's nowcasts. So the current presentation method is a static PDF released once a quarter. But if you think about kind of the value of a nowcast and how a nice way to interact with them, it's really more to give you an ongoing view of how the situation is developing over time. And these periodic distribution structure is not really as conducive to that. When people see, okay, the nowcast is released, it says this number, people think that that's the number, and that's what UNCTAD is nowcasting, when really, as we saw from that Fed example, it's a number that develops over time. So to have something that's a living website that people can check periodically and see how the narrative changes over time is, I think, highly valuable and a better way to get utility out of the same model. So what we did at UNCTAD is developed a bouquet application as a proof of concept, which shows largely very similar to how that Fed website is working. And then I took that prototype and now working with UNCTAD developers to create a more polished version to eventually be incorporated into UNCTAD Stat as a standalone nowcast page. So that's work that's ongoing right now. So it's not yet complete, so you can't see the final product, but hopefully in the coming months, there will be some sort of release where you can basically interact much more freely with UNCTAD's nowcasts, see prior years, prior quarters, and get a more interactive look at that product. So are there any questions on kind of that final data product aspect before I move on to the conclusion?
Sorry, there is always a question about previous slides.
Sure.
So there is a question about also building on what Frank asked. Do the explanatory variable change at each run, or the set is fixed now and you will reevaluate in October?
Right. So exactly that. It's that the variables are set as well as the hyperparameters. So the retraining that happens on a quarterly basis is just to give the data the latest information. So so if we're in Q4 2021, it's now going to be able to have some information from the third quarter when it's making its predictions on the fourth quarter. So it's just updating the data that's fed into the model. The actual variables and hyperparameters that go into the model, those are static for that year until the reassessment, annual reassessment, more kind of comprehensive reassessment of the model. And at that time, it could change the explanatory variables and the hyperparameters. But in that intra-year period, each quarter, everything is staying the same. You're just giving the model more information, so the latest information. That's how that process plays out. And obviously, how often this happens and how comprehensive it is going to depend a lot on your application. So if we're talking about, Facebook's algorithm, machine learning algorithm for the newsfeed, that's probably retrained. I don't know, depending on how big it is. It could be every hour, depending on how it works, or if it's a huge thing, maybe every month. But it really depends totally on the use case, and you have to kind of experiment and see what makes the most sense. So for our case, what I could also do to analyze whether or not this quarterly data update is sufficient is to compare the model from Q1 2020 to the model from Q3 2021, and then see how they compare and if there's any drift and if there's any value add from training it on the latest information, or if maybe it doesn't need to be fed new information that often, and really the whole year it could go without being retrained, and it can just be part of this exercise of reevaluating the input variables. So that's just kind of a heuristic topic that depends on the application. So finally, I will just kind of reiterate everything that I went through. Hopefully everything was clear, but kind of the big takeaway that I'll say from this is that if you have not performed a machine learning exercise before, it can sound very daunting. And if you look at this presentation as a whole, you might think that that sounds like a lot. And it is a lot, but at the same time, at the end of the day, if you break down each of those steps into its constituent parts, each step is very doable and pretty straightforward. So just focus on each individual step. And if you do that and don't get kind of intimidated by the whole process, you'll see that it's actually not that hard to get something useful out of a machine learning exercise. So what those parts are, again, in my experience, if anybody wants to add anything or say that this approach is better in the discussion afterwards, please feel free. It's just my experience. Starting out by assessing your problem, choosing the methods that could be applicable to this problem, and writing out your outline of what you're trying to accomplish with this, what your final goal is, etc. Getting your data and getting it in the proper format for your model, running your models and saving the outputs of all your different models, analyzing the results of those model runs, and then finally writing up the results into a paper or a report. And then if you want to go a step further, you can package the code that you used for your model into a library. And if you want to go even further, you can work with either developers or on your own if you want to make a proof of concept or a prototype to create a more involved data product at the end. And a couple other main takeaways that I always keep in mind when I'm performing projects like this is to always think about myself in the future as well as third parties when I'm doing this project. So avoiding the kind of impulse or the urge to take shortcuts or write overly specific code or to repeat myself just because it's easier in that moment, and that I think that it's fine, it's just a one-time thing, I'll be able to go back and tweak it later, no big deal. I found that it's much better to invest that time up front into writing code that is as general and modular as possible, and making anything specific to your project just be parameters of functions, parameters of methods, variables definable at the very beginning. And that way it's super easy to extend your project, to reproduce it later on, which is a very important thing. So say you want to do this modeling exercise this year, for example. If I hadn't had these things in mind last year when I was doing all this, I would be, very upset with myself this year, trying to parse through my code and make it work again a year on. So I think that upfront investment, and because it does take obviously a little bit more time to properly create things in functions and make things modular. But I've found that it almost always pays off later on. Even things that I never thought I'd have to go back to, I do go back, and then I curse myself when I took a lot of shortcuts, hard-coded a lot of things, repeated myself a lot, and now have to go through and make sure I didn't miss any of the 25 places where I wrote 2020 instead of 2021. That should be defined at the very beginning as, you know, target year or something like that. So those are the final thoughts I'll leave you with. Hopefully there was, you found something useful in this. Maybe if you're very experienced in the field, a lot of it was repetition for you, but maybe you found something interesting in seeing how it was applied in this particular use case. But what I'll leave here is a lot of resources of the things that I talked about in the presentation. So this is the link to the Python library for the LSTM library in Python. The same thing in R, so there's an R wrapper for it as well. The repo for the R implementation of dynamic factor models. I guess maybe I don't have it here, but I'll add it later on before we distribute this PowerPoint. Then the resulting UNCTAD research paper on LSTM's performance and as it compared to dynamic factor models. Hopefully this will answer one of the questions earlier on about how this approach actually did in the end. This is the UNCTAD research paper on dynamic factor models that Fernando Cantu wrote, which was providing the context of dynamic factor models for this work on international trade. And then finally, a link to a UNSD brown bag where I talk specifically about this LSTM exercise. So if you want more detail but aren't as interested in actually reading the paper, you can have a look at that brown bag and get a lot more of the specifics on this nowcasting project and not just as it related to these overarching principles. So that's where I'll leave it in terms of my content. I hope the time is okay, but hopefully we have some time for, ooh, it's pretty late. So hopefully we have time for discussion.
Great, thank you so much, Daniel. That was a really fantastic, comprehensive overview. And I think particularly that those of us who are quite new to machine learning and data science, that there's really so much that's sort of very accessible there, and I think really does help demystify the whole process. We've only got a few minutes left of the formal session before we close. So In-Kyung's putting up a few questions there on the screen for the general discussion in the chat, which is great. So yeah, perhaps is there anything you'd like to pick up on there, Daniel?
Yeah, so they're both kind of related, and it's a really important aspect of what I talked about, this idea of remote hosting and yeah, having these living models. And really depends on how your organization works and what works for you. So when I was in the private sector, obviously we have AWS. At one of the places I worked, we had Google Cloud Provider at another one, and you can set up your code there. Different cloud providers have different. So Amazon has a specific, you know, machine learning implementation that's made to work in their environment. But at the same time, you can also just get servers, just a computer basically, where you can just plop your code itself and have it run there. And that's where this aspect of what I talked about, making sure your stuff is generalizable, making sure that it can be automated and run from start to finish on an environment, making sure you've defined the environment where the model has to run very well by having a requirements.txt. If you have, if you're using Python, there's another implementation for R. Because if you want it to run on a server, it has to be able to run not just on your local machine with your local libraries that you have installed. It needs to be reproducible on a, basically imagine that you had a brand new PC out of the box and you need to make your project work on it. That has to be kind of defined and doable. As far as the provider you use for it, it may not even be a cloud provider. It could be your internal server if you have one at your organization, and that will just be coordinating with IT and saying, hey, I have this block of code I need to run on a whatever weekly basis. Do you have can you help me out in getting that on a server? So as long as you have your project working seamlessly on any machine, so in a way that you could go to your colleague's machine and have it running as well, you're going to be in good business because it's going to be the same process on the server. What I will say is that it's usually servers are Linux-based operating systems. So things like file path, etc., may need to be tweaked if it's going to be on a Unix-based machine versus a Windows-based machine. Of course, there are Windows servers, but they're usually kind of more expensive if you're going with Amazon, etc. But if absolutely necessary, you can, of course, find Windows servers. But just to mention that a lot of these things are happening in Linux. And then in that regard, how can I get this into production and have the model kind of live peacefully doing its thing on the server? That's just, again, making sure you've written your code well and that the process can just run from start to finish. Everything is going off of APIs, etc. And you don't need to do anything but check in once in a while, have some error reporting if something breaks, but you don't actually have to go into the server. And another tool that's often used for this exact kind of problem is Docker. So Docker is a way that you have kind of a mini computer where you create the whole process inside of a Docker container, and then you can deploy that container on any computer that has Docker on it. That's a pretty nice and elegant way to get these projects productionized. So it's Docker if you want to look into it, but you do have some kind of knowledge of the command line and how things like that work. So it might be a little difficult for you if you haven't worked with that stuff before. But beyond that, I think if you work with your tech team and your IT department, explaining what it is you want, I want this kind of code pipeline to be sitting on the server and updated automatically, they can probably help you out with making that happen.
Great, thank you, Daniel. And I think, would you like to say anything more about the question that came up earlier about the sort of difference in performance between the different models that you were using?
Sure. So I know the official time is about to run out, but I'm happy to stay some minutes after if anybody has to leave already. Feel free, but I'm happy to stay for a couple more minutes. So I don't know if you have to do some official close the recording.
Yes, well, if I can just wrap up then now, just for those who do have to go, just to formally thank you very much, Daniel, for this excellent presentation today, and it was really great to be able to sort of have the benefit of all your experience and innovative work. And I think particularly we are very appreciative of the points you made around how to develop applications that can then be generalizable and shareable among the wider official statistics community. And that's really something that we at the Data Science Campus and ML 2021 group really want to encourage. So thanks very much to you, Daniel. Again, thanks to everyone for attending.